So this is a lesson on velocity and other rates of change, specifically particle motion. You can follow along in page 16 of your in your packet and take some notes. So first we're going to talk about what particle motion is. Particle motion is linear motion of an object, and it's basically the motion of an object along a line. So it could be, for example, a bug walking along a fence, and that would be in the horizontal direction. Or it could be a particle, whatever particle that is, moving in the vertical direction. But it's the motion of an object in a linear direction, whether that be horizontal or vertical. Okay? So usually when you are doing a particle motion problem, they'll give you an equation for the position. And sometimes it's represented as s of t, a function s with respect to t, or sometimes x of t, or sometimes p of t. Okay, these are all functions that represent the position. So the position of a particle represented p of t. This is where the particle is at time t. What's the position of the particle on the x-axis at time t? What's the position of the particle on the y-axis at time t? Okay, this position could be equal to -1. So that would represent that the particle is at the location -1 at time, for example, 0. If you take the derivative of the position, function, that's going to give you the velocity of the particle. And again, if you take the second derivative of the position function, or the derivative of the velocity, that's going to give you the acceleration of the particle. If we had to represent these values with units, for example, position would be represented in, let's say, feet. If I take the derivative of the position, that will give me the velocity. The velocity of an object is units per time, or for example, feet per second. And if I took the derivative again, I get feet per second again, which means per second squared. These are generally the units that we use for position, velocity, and acceleration. You're probably more familiar with velocity in terms of driving a car, miles per hour. If you took the derivative of the velocity, it would give you the acceleration, miles per hour squared. So this example, again, is on page 16 of your packet. Okay, we have a particle, it's moving along the x-axis. So this is horizontal linear position, linear motion. And it's moving from on the interval from 0 to 9 seconds. And its position is given by this equation in terms of t, in terms of time. And time here is in seconds. So for example, if I wanted to know what's the position of the particle at time 0, where is the particle on the x-axis when the time is 0, I would plug in 0 here, here, and here. So that would give me 0 minus 0 plus 0 minus 27. So the position of the particle at time 0 is -27. So it's at -27 on the x-axis at time equals 0. Here's the first question. Find the displacement. Displacement is change in position. and it's asking me for the displacement in the first 4 seconds. Okay, so displacement is equal to change in position. Change in position. So displacement is equal to change in position. So here they're talking about the first 4 seconds. So if I had to describe the interval that they're talking about, they're talking from 0 to 4 seconds. Okay, and we want to know displacement in general is the change in position on the interval from A to B. And if I want the change in position, that's going to be the position at the end minus the position at the beginning to find the displacement. How much has it moved in the first 4 seconds? Okay, so we know A equals 0 and B equals 4 for this particular case. So we need to find the position at A, which is the position of 0, which we found is negative 27. I also need to find the position at time 4, which when I plug in 4 into this equation, I get negative 11. So the displacement is the change in the position. So it would be negative 11 minus negative 27. So the displacement is 16, and we'll say 16 feet. So if I took a picture of the particle at 0 seconds, it was at negative 27 on the number line. If I took another picture of the particle at 4 seconds, it would have been at negative 11 on the x-axis. So displacement is, what's that change? How much did it change? Well, it changed 16 feet in those 4 seconds if I just look at from 0 to 4. The next thing we're going to talk about is average velocity. So average velocity is different than instantaneous velocity. Instantaneous velocity, we said, is a synonym for the derivative. Average velocity is not the derivative. Average velocity in the first 4 seconds. So again, we're looking over an interval from 0 to 4 seconds. Okay, so average velocity. Remember, velocity has units of feet per second or distance per time. So average velocity is going to be the change in position over the change in time, or the displacement over the change in time. So that's going to be the position at the end minus the position at the beginning over b minus a, the change in time. So we already found these values. We said it was negative 11 minus negative 27 over 4 minus 0. And we do the math, and that's 16 over 4, which is 4. Now, I have to put units on it. I would say the average velocity in the first 4 seconds is 4 feet per second. So instantaneous velocity, this is the velocity of an object at a particular point. So this is the derivative. Okay, so we want to find the instantaneous velocity at 3 seconds. So we'd first take our equation that we had, the position equation, which was t to the 3rd power minus 12t squared plus 36t minus 27. And what we need to do is we need to find the velocity. And we said the velocity was the derivative of the position. So that's going to be 3t squared minus 24t plus 36. And we want to find the instantaneous velocity at time 3 seconds. What's the velocity? How fast is the particle moving and in what direction when time equals 3? So we plug 3 in. So 3 times 3 squared minus 24 times 3 plus 36. Do some mental math. We get -9. And the units are feet per second. Again, this is not a position, this is a velocity. It's moving -9 feet per second when the time is 3. So at time 3, the particle is moving -9 feet per second. Okay? So velocity has magnitude and direction. It's not a scalar value. It has magnitude and direction. So magnitude means that it's the value is 9. Direction is the negative. Okay? So I would say at t equals 3 seconds, when time is 3 seconds, the instantaneous velocity is -9 feet per second. Next, we're going to find the speed. Speed is different than velocity. Speed is the actual value. Speed does not indicate direction. As I said, velocity has magnitude and direction, but it still has those same units that we want for speed. So speed, in fact, is equal to the absolute value of the velocity. So in this case, the speed of the particle is equal to the absolute value of the velocity at 3 seconds. And we found the velocity at 3 seconds to be -9. So the particle is moving 9 feet per second when time equals 3. The speed of the object is 9 feet per second. Lastly, we're going to find the acceleration at t equals 3. This is the rate at which a particle is speeding up or slowing down. That's what acceleration is. So again, we start out with our position function that they gave to us. T cubed minus 12t squared plus 36t minus 27. And next we find the velocity. And we find the velocity by taking the derivative of the position. So we found that already to be 3t squared minus 24t plus 36. Lastly, to find the acceleration, that means we take the derivative of the velocity, and that's the second derivative of the position function. So I'm going to take the derivative of now this. So we get 6t minus 24. This is a function in terms of time that yields the acceleration of the particle. So the question asks, find the acceleration of the particle when time equals 3. So we're going to plug in 3. We want to find the acceleration at 3 seconds. So 6 times 3 minus 24. Do some math, and we get -6. And the units on acceleration are feet per second squared. This is a rate of a rate. This is a rate at which something is speeding up or slowing down. So at t equals 3 seconds, the acceleration of the particle is negative 6 feet per second squared. At what value of t does the particle change direction? An object changes direction when the velocity changes sign. And when does it change sign? We have to check when v of t equals 0. Okay? So we found our velocity already. The velocity function is 3t squared minus 24t plus 36, and that has to equal 0 because we want to find where the velocity equals 0. Before and after, it may change sign. So first thing I'm going to do is I'm going to solve this function and find the values where it equals 0. I can do this by I can look at these numbers and they're all divisible by 3. So I'm going to factor out the 3. So I get 3t squared minus 8t plus 12. That's a little bit more manageable to factor. So I get 3 times 2 factors. So I know this has to be t, two numbers that multiply to 12, but add to 8 would be 2 and 6. The bigger number gets this middle sign. So if that's a negative 6, this has to be a negative 2 in order to get a positive 12. So the times at which the velocity equals 0 is at 2 and at 6. So I need to check the velocity before and after those times, because if it changes sign before and after those times, then we know it has changed direction. So I'm going to set up a sign chart, and I'm going to check the sign of velocity before and after 2 and before and after 6. So a number before 2 that we could check the sign would be t equals 1. Then we check the sign between 2 and 6. We could do 3, we could do 4, we could do 5. And then again, I'm going to check right after 6 when t equals 7. So a good way to do this is you could either plug into the factored form. That's the easiest. Or you plug this equation into your calculator, but again, we're not using calculators right now. So I'm going to plug into the factored form, which is the easiest form to check signs. 3 is always going to be a positive factor, times, if I plug 1 in here, I get 1 minus 2, which is negative. In the last factor, I plug in 1, and I get 1 minus 6, which is also negative. Now, if I consolidate this, positive times a negative gives me a negative, and I bring down this negative over here. A negative times a negative is a positive value. So before t equals 2, we have positive velocity. We want to check to make sure the sign changes after 2, because when the sign changes, the object is changing direction. So I'm going to plug in 3 into the factored form. This 3 is always going to be a positive factor. It's a positive 3. Plug in 3. 3 minus 2 is going to be a positive factor. Plug in 3. 3 minus 6 is going to be a negative factor. So a positive times a positive times a negative is going to be a negative. So in fact, it did change sign. Therefore, the particle is going to change direction when time equals 2. Let's check when time equals 6. Plug in 7. This 3 is always going to be a positive factor. Times 7 minus 2 is positive, and 7 minus 6 is also a positive answer. I have a positive times a positive, which yields a positive. So again, at 6, it changed signs again. Therefore, the particle changed direction at 6. So my answer to this question is at t equals 2 and 6, the object changes direction because v of t changes sign, and v of t equals 0. It's very important for AP students to explain their answer.